En premier, français. En anglais, en fait. Non mais sérieusement, c'est que... Okay. So, hello everyone, my name is Alexandre Maurer. I'm a PhD student of Sébastien-Tixeuil, and I'm going to present you my PhD works on the topic tolerating Byzantine failures in sparse networks. So first, let me explain the context. So it's about broadcasting information in a multihop network. That is a network that is not totally connected and where some node must rely on other node to communicate. So in this very simple example, let us suppose that the node A wants to broadcast a message blue. Then first it will send it to its neighbor B, that in turn will transmit it to its neighbor C. And eventually the node C will know that A says blue. But now the problem is, can we always rely on this intermediary node B? Well, this is not always the case because sometimes the nodes can be subject to attacks, failures, memory corruptions, bit flips. And in order to encompass the most general possible model of failure, we are going to study the Byzantine model, where the failing nodes are of totally arbitrary behavior. So here, for instance, the node B could broadcast a message pretending that A says red to make the node C believe that A says red. And we can see that these Byzantine failures are extremely dangerous because one single Byzantine failure, if not neutralized, can potentially lie to the entire network. So in the following, our goal will be to design a broadcast protocol that tolerate the presence of Byzantine failures. So here is the outline of the presentation. So first we are going to present the existing works on the topic. Then we are going to present our three current contributions. So the control zone method, the fractal method, and the trigger method. So let us start with the related works. So there are two main approaches to deal with Byzantine failures. So the first one is cryptography, which has many advantages, but we will not study it for the three following reasons. So the first is that if we really want to consider Byzantine failure in the strong sense of the term, we have to assume that they know every password. Then in some network with low capacity, it may be difficult to manipulate asymmetric cryptography. But the main reason is that to use cryptography, you initially require a centralized infrastructure to initially distribute cryptographic keys. And if this initial infrastructure fails, the whole system fails. And here we would like to have a system where every component, every elementary component can fail without compromising the whole system. So for this reason, we will focus on the other approach, so the voting systems. So here the idea is to assume that there is only a small minority of Byzantine failures, and therefore if the correct node constitute themselves into a voting system, they will be able to mask the effect of Byzantine failures. So a first solution is to perform what we call a local vote. So the idea is that to retransmit a message, this node must receive it not from just one neighbor, but from 2, 3, 4 neighbors. And here, for instance, if this node happens to have only one Byzantine neighbor, well, this neighbor will never manage to broadcast a false message. So another strategy is to perform a vote on multiple paths. So that is to generate several node disjoint paths between the source and the sink. And here again, if one path happens to be corrupted by a Byzantine node, well, this is unimportant because we still have a majority of correct votes. So now that we have seen the existing solution, we would like to consider the following problem. So what happens on a sparse network? So for instance, a grid where each node has at most 4 neighbors. So first, the local vote, well, simply does not work because the grid is not sufficiently connected, so the message does not broadcast. And the vote on multiple paths actually works, but tolerates at most one Byzantine failures. because as there is at most 4 paths to one node, if you have 2 Byzantine failures, they can generate 2 false paths to any nodes, and these nodes never know what to decide. So this leads us to our global objective. So it's to design algorithms that tolerate many Byzantine failures on the grid and other sparse networks. So in other loosely connected networks. So let us present our first solution, so the control zone methods. So what is a control zone? Well, it's formed by a connected subset of nodes that we call core, and another set also connected that performs a node cut on this core that we call the border. The idea is that any node of the core must rely on a node of the border to communicate. So how does it work? Well, let us suppose that one outer node wants to broadcast a message PM0. That is a message claiming that a node named P wants to broadcast the message M0. Then when this message arrives on the border of the control zones, 2 things happen. The first is that it continues broadcasting in the core of the control zone, but it also broadcasts what we call an authorization message on the border. And the idea is that to exit the control zone, the message that went into the core must receive this authorization in order to exit the control zone. And the underlying idea is the following. It's that if one Byzantine node happens to be in the core of a control zone with the correct border, and that it tries, for instance, to broadcast a false message PM1, so a message claiming that the node P broadcasts the message M1, which is false, then this false message will never get the authorization to exit the control zone as it never entered it. And the idea is to define not just one, but a large number of control zones intersecting each other in order to filter at the maximum the diffusion of false messages. So in our paper, we propose a methodology to determine what we call a reliable node set. So that is a set of nodes, so here in blue, that will always communicate reliably pairwise, independently of the order of execution and of the behavior of Byzantine failures. And we use this to perform then in the following experimentation, because remember that it's very difficult to perform experimentation with Byzantine failures by simulating the protocol directly, because first it would imply to make hypotheses on the order of execution and above all on the behavior of Byzantine nodes, which would be far too restrictive. So in order not to make this restrictive hypothesis, we use this methodology that for a given set of Byzantine nodes, we can determine the exact set of nodes that always communicate reliably. So we perform experimentation on 100 by 100 grid with the Monte Carlo method. So the idea is to generate a large number of distribution of Byzantine failures, and in output to get the mean communication probability between 2 nodes. So as it is a square grid, we use the square control zones, so of whites 1, 2, 3. And in order to modulate the number of control zones in the network, we define a parameter that we call the order. So for instance, if we run the protocol at order 3, it means that we use all square control zones of whites 3, 2, and 1. If we run at order 4, we use all control zones of whites 4, 3, 2, 1. And here are the results. So we represented the communication probability between 2 nodes varying the number of Byzantine failures, so randomly distributed. And we notice the following phenomenon. So here we represented the plots for different orders. So here each time we increase the number of control zones. So in the first time when we increase the number of control zones, in the first time it improves the performances. But if we continue increasing it over order 3, then it decreases the performances. So the reason is that when you increase the number of control zones, well, you increase the probability to neutralize Byzantine failures. but in the same time, you give weapons to the Byzantine nodes to complicate the diffusion of correct messages. So it's double-edged. And therefore, there seems to exist an optimal number of control zones in this network. And in yellow, we represented the performances of the vote on multiple paths, so the only solution that works on a grid. And for instance, if we want a communication probability of 99%, well, our protocol is 10 times more effective. So now let us see the second contribution, so what we call the fractal method. So it starts with the following problem. It's that consider a grid with a uniform rate of Byzantine failures. That is that each node has the same probability lambda to be Byzantine. And with all existing solutions, so including the control zones, we have the following problem. It's that when we increase the size of the grid with a constant Byzantine rate, then the communication probability eventually falls to 0. So the reason is the following. It's that for each existing solution, there exists a critical scheme, a critical configuration of Byzantine failures. And if this critical set exists anywhere in the grid, there may be an explosion of Byzantine message and it's game over. So the thing is that for fixed Byzantine rate, if we keep increasing the size of the grid, then the probability to have this configuration somewhere in the grid approaches 1, and therefore the communication probability approaches 0. And what we propose here is the first solution for which there exists a lower bound on the communication probability. So therefore, even if we build a grid that becomes as large as the universe, then we will still have a communication probability of 0.9999. So how does it work? So the idea is to define a fractal algorithm. So first we define a sequence of a grid gk, so gk being 10 power k times 10 power k grid. And the idea is that on a G1 we use an existing protocol, so for instance the control zone protocol, and then we use the protocol on a gk to define the protocol on a gk plus 1. So it's a kind of inductive definition. So more precisely, here we represented gk and gk plus 1. And the idea is that to each node p of gk, we associate what we call a macro node gp, which is a cluster of nodes which also happens to be a grid. And the idea is that this macro node must correctly simulate the behavior of the node on the grid gk. So for instance, let us suppose that we want to perform a simple message spacing on a gk. Well, here is how it will be simulated on gk plus 1. Then first the source will broadcast the message in its cluster. Then when this message arrives on the border, it is transmitted to its neighbor in the second cluster, then rebroadcasted. And then when it arrives on the second border, we must wait that we receive a strict majority of messages. And then we continue the broadcast. And the idea, of course, is that there is only, let's say, 2 or 3 Byzantine failures in a macro node. Well, this is unimportant because they are masked by the number of correct votes. And here is our result. So here it's not an experimental but a theoretical result. So if lambda is the Byzantine rate and p the communication probability, then if lambda is smaller than 0.1%, the communication probability is greater than 99.9%, and this independently of the size of the grid. So even if we have an infinitely giant grid. So the idea is to show that we can have scalable algorithm for the problem of the uniform rate of Byzantine failures. And at last, let us see the last solution, the trigger method. So here we adopt a new setting. So in the two previous solutions, we implicitly assume that the node knew their position on the grid or on the network. And here we remove this hypothesis and we consider that the node don't know their position. So the situation is perfectly symmetric between the nodes. And we are going to see what we can do, however. So we use the following algorithm. So the idea is that now to deliver a message, a node must receive it, well, first from a direct neighbor, but also from another node located at most h hops, h being a parameter of the algorithm, so by a disjoint pass. And the idea is that if the Byzantine nodes are sufficiently spaced, sufficiently distant, then they will never be able to cooperate in order to make this node deliver a false message. So more formally, we consider the following network topology. So 4 connected planar graphs. So 4 connected because at least 4 nodes must be removed to disconnect the graph, and planar because we can represent it in a bidimensional space without the crossing edge. And we put planar into brackets because we are currently trying to remove this planar hypothesis. And we have the following theoretical results. So if D is a minimal distance between Byzantine failures, and Z the size of the largest cycle, so here the cycle are the inner polygons. So for instance, here the largest cycle has 5 nodes. Then if D is greater than Z, we always achieve a reliable broadcast. So that means that first the correct node never accept false messages, but in the second time they always manage to broadcast their messages despite Byzantine failures. So this was for the theoretical part. So now let's see a more experimental aspect. So now we generalized this idea of trigger by using multiple triggers. So for instance, here in this example, to deliver the message, a node must receive it, well, first from a first pass of 3 hops, from a second pass of 4 hops, and from a last pass of 2 hops. And this setting of the protocol will therefore correspond to the triplet 3, 4, 2. But we can have any numbers and any number of numbers. So we tried to compare experimentally different settings of the protocol, so 1, 2, 1, 2, 5, and so forth. And then we observe approximately the same phenomenon that with the control zones. That is, well, when the setting is too simple, so for instance 1, 2, the performances are bad. The performances increase if we use a more complicated setting. But if the setting is too complicated, so it has too much parameters, then the performances anew decrease. So again, there seems to exist a kind of optimal setting, so not too simple but not too complicated. And at last, we made a general comparison between the algorithm. So we represented the communication probability on varying the Byzantine rate, so on a logarithmic scale. So each time we multiply the Byzantine rate by 10. So first here we represented the performances of a simple broadcast, so where we simply broadcast the message without any verification. Then the performances of the vote on multiple pass. Then the performances of the first trigger algorithm, so the simple one. Then the performances of the generalized trigger. And at last, the performances of the control zone protocol. But remember that to have this, we must make the hypothesis that the node knows their position on the network. So if we don't know our position on the network, the generalized trigger is the best solution. So in conclusion, I hope that I have convinced you that yes, we can tolerate Byzantine failure in a sparse network. And we are currently working on the following paper. So first, we would like to make the trigger method self-stabilizing. So for instance, if the network transiently experiments a lot more Byzantine failures that it can tolerate, and then that the number of Byzantine failures a new become acceptable, then can we retrieve correct outputs in how many time? And the other paper would be on dynamic networks, so a network where the topology changes endlessly. And we would like to find the necessary and sufficient conditions for reliable broadcast in a dynamic network. So I thank you for your attention, and feel free to ask any question.
I have a curiosity. Your results show that making more complex triggers, actually, the performance become worse. And have you any reasonable motivation? Any motivation on you got an idea why that happens?
Why? So it's because it's always the same principle. So the more parameter we have, so the more paths we use in the algorithm, then the more difficult it is for Byzantine failures to cooperate to make a correct node deliver a false message. But the more paths we use, then also the more complicated it becomes for the correct node to broadcast messages. So of course, if there are no Byzantine failure, it's okay. But if there are Byzantine failures, there are like holes in the networks, and holes is all the more a problem that we have a large number of paths to have.
So, a question about when you show the performance about the comparison, where you have basically this one. So I guess that here the gap between both multiple paths and control zone is large because the network is sparse. In case you have a network which is well connected, do the performance gaps really remains toward the magnitude apart, or does it become closer?
Well, I don't know, but the idea is that on a network that are not sparse, there actually exist more efficient solutions that the two that were presented, so local vote and vote on multiple paths. And the interest of this solution are only for sparse network, because for sparse network, none of the existing solutions work with satisfying performances. So we could, of course, try to see what it makes on a dense network, but it would not have motivation, I think. So. No, yeah.
Just one curiosity, especially on the first solution you gave, the overhead might be very big, right? Because you have to send a lot of messages. The first solution.
Well,
yeah, if I understood correctly, for each message you send, you also have to send these control messages around this border, right?
Yes, but for instance, if we make a simple broadcast, then each node, so if in is the number of nodes, each node, we will have around in messages in the global network. So it's with a simple broadcast. And here we have k times in messages. So it's for instance 100 times in, but it's still proportional to the number of nodes. So it's not exponential or stuff like that. But it's however it's exponential with the order of the protocol. So if the number of messages increase exponentially if we increase the order.
Just a question about, so when you say order k, you are using all the borders with smaller or equal than k.
Yes.
Right. So is there any reason to use all the others that are smaller or equal and not using only those who are exactly equal to k?
Or not to use what?
Only the things that are k.
What we do, we use the smaller control zones than k.
Yeah.
So it's because, for instance, if we want to, how to put it? In terms of safety, so not to have a correct node delivering a false message. So the more control zone we use, the better it is. So we have interest to use also the small control zones. But in order of what we call reliability, so to successfully broadcast the correct message despite Byzantine failure, well, if we manage to do this with the largest control zone, we implicitly also manage to do it with a small one. And so we have no reason not to use it because they will only increase the performances. And also, to neutralize just simple isolated Byzantine nodes, it's simpler to use these zones.
You have reason not to use it because, as you said, you increase exponentially the number of messages you send.
Yes, it's true. No, the reason is that, so as I say, so in order to broadcast the correct message, if we manage to do this with the zone of order k, we necessarily manage to do this with the zone of k minus 1. But in order to determine what we call the reliable node set, so if we only use, now for instance, if you have two Byzantine nodes that are distant for, let's say, 3 hops, if we use the small control zone of order 1, then we can we have all the nodes in blue. But if we only use a big control zone, we will have a hole between the two Byzantine nodes because no message will broadcast in the middle. So, and I mean the message in the middle will not be safe because they will be able to receive Byzantine messages with large control zones. I don't know if I'm clear.
Am I sharing this again?
I'm Jerry.